I'm gonna talk about a subject that I've been doing a bit of research on in the last couple of years that I'm very excited about, which is as you just heard, a very important topic in terms of actual commerce and in terms of its applications in practice, and also leads to very interesting research questions in theory. This is a joint work with my colleague from Georgia Tech, Alan Herrera, and the results I'm going to present here are mostly the results from a paper with one of our students, Alex. But then at the end of the, if time permits, I'm going to also present some ongoing work in a working paper with another student, Depayan. Please do feel free to interrupt and ask questions as we go. That would be perfectly fine. Just let me give you a quick motivation about e-commerce, at least e-commerce in the United States. So this is it's already a large and a growing part of retail. It's only getting bigger, and this is all pre-COVID, and of course, COVID has forced everybody to be at home, as we all are now, or as a lot of us are now. At least I'm at home, and that means that's only led to a significant jump in the growth of e-commerce. And I've heard some experts say that COVID has pushed us forward about 5 years in terms of the growth of e-commerce from where we would have been. So e-commerce is going to keep growing and eventually become essentially all of retail. And it presents a bunch of interesting challenges to the supply chain and logistics management of these systems that were not there in regular retail settings. This is just a chart showing again the growth of e-commerce. It's a really kind of a tremendous growth in the past few years, and again, this is pre-COVID. So what are the sort of the interesting aspects and the challenges of looking at same-day delivery, which is kind of let's say the cutting edge of e-commerce? The main issue is when e-commerce providers, when these e-commerce giants like Amazon in the United States want to compete, they're really competing with brick and mortar stores. So with stores that actually have physical locations. And one of the ways in which a brick and mortar store has an advantage over Amazon is the fact that if a customer goes to the store, they will get the product that they want immediately. Whereas when you order with e-commerce, there's a waiting period. And in many cases, the waiting period can be several days. And so same-day delivery is a push on the e-commerce side to try to chip away at this advantage and be able to offer many, many products to the consumer, if not immediately, then at least the same day that they order them. So this is of course, in some sense, the holy grail for e-commerce, because this would bring them in line to essentially compete directly with traditional retail. So of course, e-commerce brings with it a bunch of these challenges that I was mentioning, in particular, this notion of the last mile being extremely expensive. So the last mile is an expression in logistics. It just talks about the part of the supply chain, the part of the distribution system, the last portion of it before it reaches the consumer. And in same-day delivery, this part of the supply chain is extremely expensive because there are very, very few opportunities for economies of scale and for consolidation. If you think about it, what's going on is that in traditional retail, you can wait and accumulate orders. Let's say orders that are going to be delivered, even if it's next day orders, they will all be accumulated overnight, let's say, and you can do a lot of traditional routing to squeeze as much in terms of routing economies as you can out of the system. In e-commerce, you just can't do that. And also, there's a lot of downward pressure from the customer side, because customers have been accustomed to either free or very cheap delivery service, which means that you have to provide these services, you have to provide them quickly, and you have to provide them at very low cost. So there's lots of competing pressures lots of competing challenges that are putting downward pressure on this part of the supply chain, specifically on that last mile. And so so that just leads to lots of important questions about the management of these systems in order to be able to manage them efficiently. And so, as I was saying a second ago, in traditional delivery, so even if you're talking about next day, so overnight delivery, and of course for anything that's slower than that, it's the same thing. You will be able to do your order management at the last mile step, your order management and your order picking and your organizing of delivery routes and things like that. All of that happens before you actually have to do the delivery. So if you imagine something like for an overnight package delivery, you would have a large set of packages comes in at some point, let's say in the middle of the night, into a distribution center or a warehouse, and then they have this midnight shift up until the beginning of the day to sort and organize these packages, to divide them into delivery routes, and then to plan the delivery routes for each of the divided set of packages. And so that can happen sequentially. What happens in same-day delivery is that the arrival of orders, their acceptance, the picking, and the organization of the orders on the warehousing part, all of that happens while you already have to be doing delivery, because this is all happening simultaneously. And so that's a significant change in the dynamics of the system. That means that you can't wait until all of the information about orders is available to you to start taking action. You have to start taking action before. So I should also specify here that I am talking about the same day delivery that I'm talking about is same day delivery that offers a common end of the day guarantee. So this is not like food delivery, which is food delivery is in some sense, it's a much older distribution model, right? This is the model in which you say you order food from a restaurant that offers delivery, home delivery, and they guarantee that they will have it, they will deliver it by 30 minutes or 1 hour after you place the order, something like this. And that is let's say that's the extreme end of the delivery spectrum. And that's really not, it's too extreme in the sense that there are essentially almost no opportunities for order consolidation when you're looking at food and grocery delivery. The orders you're delivering tend to be highly perishable and time sensitive. And so you're really talking about at most 2 or 3 orders being delivered at once from the same delivery vehicle. And that means that the kinds of questions that those systems find important are different kinds of questions than what we are looking at here, where we're more concerned about the actual routing and the sort of the logistics efficiency of the system. In those systems, you're really talking more about planning to have enough capacity in terms of delivery drivers, and there's other questions that come into play. What we are concerned with are the delivery of goods that are not perishable or not as perishable. So we're not necessarily talking about meals or very perishable items like, say, something like dairy products or something that would have to be refrigerated all the time or something like this, but rather more like household goods. Like maybe one example would be, let's say, diapers for a family that has young babies, or some other kind of dried food that is non-perishable that they could wait until the end of the day to be delivered, something like this. The idea being that the model we're discussing here is a model in which a person realizes that they need something. Maybe they need soap, maybe they need diapers, something like this, but it can wait until the end of the day. And let's say in pre-COVID times, this person would realize that they need soap and they're about to leave for work, but they place an order and they just want the soap to be there when they come back from work at the end of the day. So the model would offer a common delivery guarantee of something like 5 p.m. or 7 p.m. or something like this. This is the kind of model that we're talking about. And so this is a nice illustration that I stole from my colleague Alan of why these problems are so complicated from a logistics perspective. So the top picture shows you how a traditional vehicle routing model would look at a problem like this, and how it would very compactly and efficiently organize these delivery orders to make very efficient delivery routes. But once you take into account the timing of these orders and you realize that you have a deadline by which all of the orders have to be delivered, then you're forced to make much more inefficient delivery routes like the ones you see at the bottom. So you will over and over again be sort of retracing. If you're not careful, or if you're not lucky, you will be retracing your steps and visiting the same parts of the service region that you were visiting already, simply because you're forced to, because the only way to the only way to keep up and to be able to get to make all of the deliveries by your guarantee is to just be doing work while the orders are still coming in. So this is the kind of behavior we have in mind. So I have worked in this space for, at this point, actually quite a few years now. So 5-6 years, something like this. Actually, maybe even more. And when I first started working in this area, we worked on operational models. So at the level of the actual dispatcher who's making decisions on a day-to-day basis of what to do, when to dispatch a vehicle, what orders to put on the vehicle, when to have the vehicle wait. These kinds of questions, that's actually a space that's been studied quite a bit in the logistics community. And I'm giving here some examples of representative papers that have looked at this kind of a problem from an operational angle. Now, the operational setup is really the setup in which you are really the dispatcher. Everything about the system has already been fixed, and you are just doing your best to manage the system with the resources you were given. Let me see the question here. Is the SDD problem a CVRP with time windows? Excellent question. So for those of you who are familiar with the logistics nomenclature, the deterministic version of this problem would be called a vehicle routing problem with release dates and a common deadline. So with release dates and a deadline. So you're right. Every order has the time window, all of the time windows, all of the windows for delivery for every single order all end at the same time, which is the end of the day. But what's different is that you have what are called release dates or release times, which are more common in the scheduling literature. So what this says is that if you want a route to include one particular order, the route must depart the depot after that order is available. So it's a little bit different from a time window. The time windows are really about arriving at the customer location within those times, whereas the release time tells you that you cannot include this order in this route unless the route leaves the warehouse after the order is available. That's an excellent question, and we'll get to the specifics of my model in a second. But the examples that I'm showing here of operational models are models that the deterministic versions of them look very much like the model that I just described. It tends to be lots of models that have a routing component, but also have a timing component, usually in the form of release times and deadlines. And on top of it, in reality, there's a high level of uncertainty in these models. So what's going on is that you have both uncertainty and dynamism in terms of what you have to do. You're making decisions all the time. The dispatcher constantly has to decide what orders to what orders to serve, how to organize them, and things like this. And then there's without having full knowledge of what's going to happen in the future, and having to maybe anticipate or guess what might happen in the future. And so that's one of the things that makes these models very, very difficult to solve. They really can only be solved heuristically. And if you're trying to decide what like how many vehicles to dedicate to your delivery fleet or how late in the day to offer the service. These models are very difficult for that purpose because they're not very transparent in terms of giving you answers. So what we want to do in this research is really look at the problem at a simplified level, much higher up, and try to capture not what would happen on any given day, but more try to capture the average behavior of the system. And because the model is much simpler, then be able to extract managerial insights on it and be able to decide, how late in the day to offer the service or how many vehicles to dedicate to the delivery fleet and these kinds of questions. So that's really the goal of this talk. So for the rest of the talk, that's basically what I'm going to do is I'm actually going to present to you the model that we used, that we proposed. And once I explain how the model works and how to solve it, then I'll give you some examples of how we would use that model to make actual tactical design decisions. So for example, should we, how many vehicles should we use for the delivery in this particular region, something like this. And then the last thing is this is a very simplified model of these operations. And so we are really relying on the model to be accurate in order for the decisions that we make with it to really reflect reality. And so I'm also going to show you a computational validation that demonstrates that even though the model is very simple, it's quite simplified, that it does accurately reflect what will happen, what will happen in practice. And then, and like I said, if we have time, I'll talk a little bit about ongoing work. So, the model is very simple, and you only need a few concepts to understand it, a few parameters to understand it. The first things you need are, so the way that the system works is that the day starts at time 0, and you accept orders until time capital N, and all orders must be delivered and the vehicles must return to the depot by time capital T. So T is the service guarantee that you offer. And so what you basically, if you can imagine here what N and T would be, N and T would say something like, if N is 3 p.m. and T is 6 p.m., what you would say is, if you place your order by 3 p.m., you get your order delivered by 6 p.m. That's the way that the system works. We assume that there's going to be a constant arrival of orders over the course of the service day. So in our model, this is going to be just a constant order arrival. So you can imagine here we're simplifying, let's say, a Poisson arrival by just saying that we have a constant arrival of orders throughout the day. So for those of you who are familiar with stochastic models, this might be like what you would call a fluid approximation. So we're just going to assume just a constant, steady arrival of orders throughout the day, and what all of the orders must be served. So the objective, in other words, you advertise that all of the orders that are placed by time N, by 3 p.m., must be delivered by time T, say 6 p.m. So because all orders must be served, the objective is going to be to serve the orders at minimum cost. That's the objective. And so the last concept that you need to understand the model is the actual dispatching function. So there's a dispatching time function, which says, so as orders accumulate, the dispatcher at some point will decide to execute a dispatch that includes a certain number of orders. And if the dispatcher decides to serve a little n number of orders, this will take some time f of n. And we're going to make the function very, very generic and simply say that f is increasing but concave. In other words, serving more orders takes more time, but there are economies of scale in serving more orders. So the more orders I serve, the less time an incremental order adds to the dispatch, okay? And there's some technical conditions. So of course, serving no orders takes no time. And then there's a technical condition about that we need for some of our results about the dispatcher, the order dispatch function needing to keep up, which basically just means that if I serve a large enough number of orders, when I come back, I will expect fewer orders to have accumulated than the orders that I served. That's what keeping up means. And the motivating function that we've got in mind here, and if you want to just have a concrete example in mind, this is the one you want to keep in mind. It's a function that looks like this. This function has three terms. So the first term is what you would call like a setup time. This is the time it takes to maybe set the vehicle up for delivery at the warehouse. It might also include if the service region is geographically removed from the warehouse, it might include the travel time from the warehouse to the service region. Then there's a linear term, which is the time it takes to make an actual delivery. So this would be, let's say, the time it takes for the vehicle to park and for the delivery person to get out and walk the order to the door. And then there's the square root term, which is what's known as a routing time approximation, and this is based on a classical result from Beardwood, Halton, and Hammersley, which I will talk about more in a second. But essentially, the assumption here is if you've got a geographically dispersed service region and you sample order locations randomly from this service region, and the distribution is continuous in the service region, then the expected routing time of a traveling salesman tour through these points, starting and ending at the depot, scales with the square root of the number of orders. Okay. If you haven't seen that before, I'm gonna talk about that in a little more depth in a second. But this is the basic idea. The basic idea is that I have a dispatching time function that includes a setup time, a service time, and a routing time, and we are also assuming here that the dispatch time is proportional to the cost of executing dispatches. So for example, this would be if there are labor costs involved with the personnel that do the delivery people and the people at the warehouse that do the loading. It could also be just because these labor costs, and maybe there's also some fuel costs or something else like that involved. So we're essentially going to be minimizing the total dispatch time. And I should also point out that this is not a new idea. These kinds of let's say routing time approximations, specifically the square root term, is something that's widely used in logistics, and very recently it's starting to get used quite a bit in urban logistics specifically, which is the kind of setting that we're in. So let me talk a little bit more about this routing time approximation. So imagine not in a realistic example, but in just a textbook example, imagine that I give you a unit square and I sample points from the uniform distribution over this unit square, and I have a depot in the center of the square. And the time it takes to the driving distance or the driving time is proportional to the rectilinear distance between the points. So as I'm giving in this example here, if I want to go from point A to point B, I have to move only in horizontal and vertical movements, which this represents the movements in a city where you would expect a street grid. And so if you have this kind of an assumption, if I assume that I sample roughly 30 locations to visit from the depot, then the expected length of the traveling salesman tour through these points, starting and ending at the depot, scales roughly with 1.04 times the square root of the number of points. For those of you who are familiar with the actual BHH theorems, the asymptotic constant in this case, as n goes to infinity, is actually closer to 0.89. But we are interested in a regime which is far, far away from the asymptotic limit. We're interested in a regime in which the number of orders is large, but the number of orders that you would deliver in a same day delivery setting. So something like maybe 30, maybe 60, something like this. So we use a bigger constant, something like 1.04 instead of 0.89. So again, we're not claiming that the actual time that it takes for a particular delivery on a particular day will be proportional to the square root of the number of orders delivered. It's in expectation. So on average, if we assume that these orders are sampled from our service region according to some probability distribution, then on average, the time it takes to make that delivery, the driving time, the routing time of that delivery scales with the square root of the number of orders. So let me give you a more realistic situation to sort of explain how this would look in our model for an actual, an actual service region. So imagine that I have a service region centered, or a square service region with a depot in the center, which is 8 miles by 8 miles, or roughly, let's say 13 by 13 kilometers. And the vehicle drives, again, making rectilinear movements at roughly 25 miles per hour between locations. And this is roughly 40 kilometers an hour. And if we assume that the orders arrive at a rate of 1 every 6 minutes, then what we're going to do is we're going to normalize everything so that the time is measured in the units that constitute the time between one order. So in this case, this would be in units of 6 minutes. And so if we include a 5-minute setup time and 2 minutes of delivery time per order, then our routing time, our dispatch time approximation looks like this function at the bottom. So we divide everything by 6 because we are measuring the time in increments of 6 minutes. And then we've got this, we've got a setup time, then we've got a service time, and then we've got this routing time approximation. So hopefully that the setup is clear and the type of routing function we're using is clear. So again, so now if you think of this just as an abstract model, what I've got is I've got three parameters define my model. I've got the order cutoff time, capital N. I've got the deadline, capital T. And I've got the function f that specifies what is my what is the time to make a certain number, to dispatch a certain number of orders. And what I want to do is minimize the total dispatching time it takes to serve all orders. And the key, it's not a it's once you think about it, the issue here is the function's concavity is going to drive you toward extremes. So of course, this example that I'm showing here is what if you split the orders in this day exactly in half and made one dispatch halfway through the accumulation time, and then made another dispatch at the end of the day, right? So you would have a setup that looks like this, but this is the most balanced dispatch possible between two, the most balanced way of dispatching orders between two dispatches, which is actually the worst you can do because of concavity. Concavity actually wants you to have unbalanced dispatching. So what you really want is something that looks a lot more like this. So if you have two delivery vehicles, what you really want is you want the first dispatch, the blue dispatch, to steal away as much as possible from the red dispatch to become as big as possible. Because the aggregate dispatch time of the two dispatches in this second case is much smaller than the aggregate dispatch time of the two separate dispatches that are as balanced as possible. And of course, you can claim, well, in this first example, I can do the two dispatches with one vehicle because the first dispatch comes back before the second one leaves, and I can't do that in this second example. So even if you only have one vehicle, you're still better off making the dispatches as unbalanced as possible. In that case, by simply having the blue dispatch take more and more of the red dispatch until its return time exactly coincides with the start time of the next dispatch. And that would be this third example. So whatever the case, whether you have many vehicles or you only have one, you want the structure of your dispatch of your dispatches to be as unbalanced as possible. Okay, and this is just purely a consequence of the concavity assumption. Okay, so hopefully this is clear. I'm not going to get into technical details of how we prove things, but this is the intuition behind basically all of our proofs. And so this structure basically gives us a lot of the intuition that we're going to use to analyze our model. One of the things that I hopefully you all notice is in these examples is that in these two latter cases, the dispatches start long and get shorter as the day goes on. So if you think about what this means in practice, what this means is at the beginning of the day, when I have more time until my deadline, I can allow more orders to accumulate, and I can therefore accumulate, because I'm accumulating more orders, be more efficient in my routing. But at the end of the day, whatever's left over, I will just have to route in whatever way I can, and I may have to be less efficient, right? So I will have an initial dispatch which is long and hopefully more efficient, and then later dispatches will get shorter and less efficient as I go. And we actually have already observed this empirically in some of our operational models. So this is a nice sort of a confirmation of our empirical observations. The other thing to notice in the structure of the examples that I just showed you is that the day is divided into a non-active and an active portion for all of the delivery vehicles. In other words, once the in operation until the end of the service day. And this is really useful because this means that if you're doing shift scheduling for your delivery drivers, that you can actually have them, they don't have to come in at the beginning of the day when the process starts. You know that once you schedule them to come in, they will essentially be busy until the end of the day. So they will be well utilized. And finally, in all of these solutions, the way that this works is that each dispatch just takes all of the orders that have shown up to this point. And this is a pretty convenient and sort of operationally simple way of thinking of the organizing of the dispatching schedule. Now, of course, this is a consequence of our model in which we do not allow geographic discrimination of orders. So of course, everything that I've showed you here is under the assumption that every order is indistinguishable to the dispatcher. But of course, in practice, that would not be the case. In practice, the dispatcher can actually observe that some orders are going to be showing up here, some orders are going to be showing up over there. And that actually means that in practice, the dispatcher could make some fine-tuning adjustments and possibly skip some orders and leave them for later. Or do some other kinds of geographic discrimination, which our model does not allow. However, that's why I'm sort of want to underline that this model is really for tactical design, and you would then at the operational level want to do further improvements like the ones I just described to actually get as good of a performance out of your system as you can. However, in the computational study that I'm going to talk about later, we'll see that the model is still very accurately tracking the best that you can do in practice. Okay, so then now let me shift to actually talking about the behavior of the system under a couple of different conditions. So the first condition I'm gonna talk about is the simplest case, which is, let's suppose that we have dedicated a vehicle fleet that is large enough for this service such that, let me see if I have a question here. Yeah. Oh, this is an excellent question. It's like, what if, so of course there are many cities, and I imagine Tehran is one of them, in which you have parts of cities that are very congested, or you have very narrow streets, or there are and oftentimes it's even actually regulations within cities where you say, there are certain neighborhoods that can only be served by smaller vehicles, or it might even be the case that for physical restrictions, you just have to do this, right? You can only send, let's say, small delivery vans or motorcycles to some parts of the city, and you can send bigger vehicles to others. So this is an excellent point. Our model is assuming a homogeneous fleet. So if you have multiple vehicles, they're homogeneous. However, what would really happen in your case is that we are assuming here that the service region has been predefined. So where the vehicles travel is already defined ahead of time. And I think your question would actually have to come before, and I'm going to talk about that a little bit at the end. When you're actually designing the service regions, you would have to do some dividing, and in your case, you would probably have to do the dividing of the service region taking into account these kinds of restrictions, right? The fact that one kind of vehicle can be used here, but a different kind of vehicle must be used over here. So you would probably want to make those divisions ahead of time. But that's an excellent question. So then if there's the simplest case for our model is, what if you assume that that you have dedicated as many vehicles as necessary to the service, such that every vehicle makes exactly one dispatch. Okay. In that case, the solution of the simple and the behavior, the solution of the system and the behavior of the system is quite simple. What happens is every vehicle takes all the available orders such that it can return exactly by the deadline. So, for example, the first dispatch in this example waits until this time T1, at which the orders that accumulate up to T1 plus the time it takes to return exactly equals the deadline. So T1 plus f of T1 equals capital T. And then your behavior is recursive. The next vehicle, again, lets orders accumulate until exactly the point at which it can leave and return precisely at the deadline. So the next vehicle, its dispatch would look like this, where it leaves at T2, where T2 is the time at which the orders that have accumulated since T1, the time it takes to dispatch those orders, plus the departure time T2, exactly equal T. And you repeat this until the last vehicle can take all the remaining orders. So in this case, the third dispatch would accumulate all the remaining orders and have, in this case, a little bit of slack left, and then depart and to return right at time T. So this is what the behavior looks like in the many vehicle case. In the one vehicle case, the behavior is a little more complicated, but not much. What you have to exploit is that structure that I mentioned before. So in this case, meaning we make sure that every time the vehicle leaves, it just takes all of the orders that have accumulated. There is no waiting between dispatches. So once the vehicle starts dispatching, it continually dispatches until the end of the day, and the last dispatch returns exactly at the end of the day. I should mention here that we have a small technical assumption here which helps us avoid pathological solutions, which is that no dispatch except the last one possibly can leave with a very, very tiny, with a small number of orders. Otherwise, we have situations in which you could have an infinitesimally small dispatch first and then a large dispatch second, which is kind of let's say, a pathological and not very useful solution to the model. So we make the assumption that there's a minimum dispatch quantity that must be, that all the dispatches except possibly the last one must execute. And in that case, the solution looks like this. So I'm giving you here a solution with two dispatches. So the way that you're basically going to solve the single vehicle model is doing something like this. You're going to first guess, can I serve all orders with one dispatch? And that's the first equation. If you get a feasible answer for that equation, then you're done. But if not, then you guess that you need two dispatches, and then you go to the second equation, and you again solve the number that solves this equation, which you can do with a root finding algorithm. This is assuming if you've got if f has something like a square root form, you can solve these equations with just any standard root finding algorithm. And again, if you guess that it's 2 and you get a feasible answer, then you stop at 2. And if you don't get a feasible answer, you go up to 3, and you guess that you use three dispatches, and so forth and so on. And essentially, the reason you can do this is because if you look at the 3 conditions that we've got here at the top, once you enforce those 3 conditions, that each dispatch takes all orders, there's no waiting, and the last dispatch returns exactly at time T, at capital T, that means that the entire solution is specified by the time of the first dispatch. So all you really need to do is find this time T1 of first dispatch. So any questions so far? So for the general case, you can unfortunately no longer characterize what will happen universally in every case, because it will depend on the parameters of the model. However, we do propose, let's say, a hybrid heuristic that has a performance guarantee for one special case. So the hybrid is relatively simple. What the hybrid does is it essentially says, if I have a finite number of M vehicles in my fleet, the first M minus one are going to do exactly what the many vehicle policy would have done. And then the last vehicle serves all the remaining orders following the single vehicle policy. So in this example, I only have 2 vehicles, but I would ideally need 3 vehicles if I wanted each vehicle to make a single dispatch. Therefore, what I do is I make the first vehicle do exactly what it would do in the many vehicle case, and then the second vehicle behaves like a single vehicle policy. And so when my dispatch time function has service time and routing time, but not setup time, then this heuristic has this approximation guarantee down here. And you don't have to worry too much about the actual expression. This capital D of M is just the number of dispatches that the last vehicle makes, which in this example is 2. What you want to look at here is just that, as you would expect, this approximation ratio improves as the fleet gets larger, because of course that means that more and more of the vehicles are just following exactly what the many vehicle policy would, but the approximation guarantee decreases in quality as the last vehicle is forced to make more and more dispatches. However, in this particular case, for the example that I'm showing here M is 2 and D of the capital D for the last vehicle is also 2. So if you plug this in here, I think you get something like an approximation ratio of about 28%. So regardless of the actual function parameters, if your solution looks like this solution is within 28% of optimal for the dispatch time function that has this kind of structure. Now, I'm about to give you an actual example that shows that, of course, the performance of this kind of thing could be much better. So let me give you, the first example I'm going to give you is fleet sizing, exploiting the structure of what I've just seen for the many vehicle model versus the single vehicle model. Let's return to this service region that I talked about a little while ago. So suppose I have a service region that's a square with a depot in the center, and it's 8 by 8 miles, and we have an order arriving every 8 minutes for 10 hours. And there's a 12-hour service day. So this would be something like, maybe I accept orders from 8 a.m. to 6 p.m. and I have to deliver by 8 p.m. And I assume again that I have a rectilinear movements for my vehicle, and the vehicle moves at an average speed of 25 miles per hour. And there's a 1-minute service time per order. And if I do my analysis here, it turns out that the many vehicle policy requires 2 vehicles, each making a single dispatch, and the 2 dispatches, the first dispatch takes 64 orders and the second one takes 11, whereas for a single vehicle, the single vehicle makes 2 dispatches, and the dispatches are not quite as uneven. I have 55 and 20 orders in that case. So it turns out, though, that if I look at the actual dispatch time of these 2 solutions, the single vehicle solution only incurs an additional 4% in dispatching time. So what this means is, if I'm deciding whether I want to dedicate a second vehicle to this delivery fleet, I think I'm probably okay using just 1 vehicle, because the second vehicle only saves me about 4% in terms of operational costs. So I might as well use that second vehicle for a different purpose, or not acquire it if I don't have to buy it. Right. So this is a nice simple example of how you would use our model. Let me give you another example, which is, what if I am actually deciding what is the latest time of the day at which I offer, to accept a same-day delivery order that will be delivered at time T. So if you will recall my many vehicle example from before, let's assume that the more orders I accept, I get more revenue, and that the revenue is linear in the orders that I accept. And this was the solution that I gave you as an example for the many vehicle policy. And recall that I said that there's some slack in the time between when the third vehicle accepts orders and when it departs, because the cutoff is given at that point. So it turns out that that's never going to be an optimal order cutoff. What you really want to do, and this is not surprising, is just however many vehicles you dedicate to this service, you want to fully utilize them, and that's the optimal choice of an order cutoff. So what that means is you would consider either using only one vehicle, in which case the order cutoff is this time T1, or if you use two vehicles, the order cutoff is T2. But if you use three vehicles, the order cutoff would be T3, and so forth and so on. If you use a fourth vehicle, you would have to fully utilize it. Okay. Now, the actual optimal cutoff time is whichever one of these is the best. But the point is that it would never be optimal to partially utilize one of the vehicles. You want to utilize them as much as possible. If you have dedicated the vehicle to the service, you're going to use it as much as possible. Okay. So those are a couple of examples of how you would actually do tactical design using this model. In the interest of time, I'm not going to give you more examples, but there's other things you can do. At the end of the talk, I may talk a little bit about like using similar ideas for service region partitioning. But there's other examples of things you can do with the model. So if there are no questions, what I'm going to do next is talk about the actual computational validation. So everything I've talked about so far, there's quite a few assumptions in place in order to get our model to look the way it does. And so, of course, you have to ask yourself, if you're thinking, if you all are familiar with the very detailed vehicle routing models that are used in logistics to actually route, to actually design vehicle routes, you might be wondering, how accurate could this model really be, and how, because it's so simple, is it really is it giving me good information? And so we did a computational validation study using Atlanta. So specifically, we picked a northeastern sort of sector of Atlanta, which I'm depicting here in this picture, which is essentially the part of Atlanta that is contained within the three highways that you see in the perimeter of this region, which are two interstate highways and one state road. And this forms about one, let's say, a northeastern quadrant or a northeastern slice of the metro Atlanta region. And it's comprised by 22 census tracts, which is when the U.S. does its census, it splits areas into tracts to do the census, and this area is comprised of 22 census tracts in total. At least as of 10 years ago, we did this study with the data from the previous census because the current census is not published yet. So this is 2010 data. In 2010, this area had about 92,000 people, and so what we did is we sampled 5 representative addresses for each census tract to give us a total of 110 addresses, and then placed the depot in the northeastern corner of the region. And then we actually calculated real driving times according to the Google API, which tells you how long it takes to drive between any two locations. And after doing after calculating all of those driving times and doing some calibrations by doing some initial sampling, we calibrated the routing time function to be 24 times route n minutes. So this is the time it takes for the depot to visit n locations, to just drive from the depot to n locations and back, and doing a traveling salesman tour from the depot is proportional to 24 times route n. And we added a 10-minute setup time and a 1.5 minute service time per order. So hopefully all of that is clear. That's the setup for the model. And then we first did a study we did a study for a 2-vehicle fleet. That's all I'm gonna present in the interest of time. And so we calculated that if you have 2 vehicles, then according to our previous results, we want both vehicles to be fully utilized, and that corresponds to a cutoff time of 3:40 in the afternoon, or roughly 67 orders. And our model then predicts 389 minutes of dispatch time total. So the two dispatches together take 389 minutes and deliver almost 67 orders. And so what we're going to compare against is, what if we actually did something similar at an operational level? So we have a Poisson arrival rate of orders with a rate of 6 minutes, orders every 6 minutes. And the location of the orders is sampled according to the same distribution, meaning a distribution that's proportional to population and median income. And so what we do is, to calculate the actual routing time of the order, we then add the setup time, the service time, and we calculate the actual TSP using the Google driving times between, for the depot and all of the orders that have shown up so far. And we keep accepting orders until those three times, the setup time, the service time, and the actual TSP time, exactly match the remaining time in the day, which is the operational version of our many vehicle policy. And then, in order to get a sense for whether this is reflecting what a dispatcher might be able to accomplish in practice, we also looked at what you would call the hindsight optimal benchmark. So this goes back to the question at the beginning of the talk about what kind of a model this is. So the hindsight optimal benchmark essentially says, imagine that the dispatcher could go back at the end of the day, and knowing exactly when each order had arrived and where it had come from, if it could optimally route its two vehicles to serve all of these orders. This would essentially give you a vehicle routing problem with release times and a deadline. And so for every simulated service day, we essentially go back and we look at when and where did the orders arrive over the course of the entire day, and optimize with the benefit of hindsight. So this is essentially better than what you could do in practice, because this is giving you all of the information when you're making your decision, instead of forcing you to make decisions without all of the information. And so this is just a benchmark to examine whether our tactical and our operational model are actually reflecting what you can accomplish in practice. And so here's some results. So first, let me show you the tactical and the operational model. So here's the tactical model's predictions by dispatch and the totals. So again, the total was 67 roughly orders and 389 minutes roughly. And as you can see, the operational model, this is the sample means over 300 simulations. And the sample mean is within 1%, not just for the totals, but for each individual dispatch. And I'm not showing you, for the interest of time, the single vehicle validation, but it's very similar. And then the hindsight optimal benchmark, again, this is what can you do with the benefit of hindsight if you could optimize the entire day all at once. And we see here we're within about, I think, 4% in terms of total dispatch time. But interestingly, there is a bit of change in terms of the number of orders delivered between the first and the second dispatch. And this is actually to be expected, because if you knew at the beginning of the day exactly when and where every order was going to show up, then you know what orders are going to show up where at the end of the day. And so even though you know that the orders are going to show up there, you cannot serve them early. You still have to serve them after they arrive. But that tells you that your vehicle will have to be in certain neighborhoods at the end of the day. And so if any orders show up in the same neighborhoods at the beginning of the day, you know that you can push them off. You know that you can wait and deliver them later, because you're going to have to go to that neighborhood anyway. And so that's where you get the savings in terms of total dispatch time, because you're actually able to move a lot of the early orders to the end of the day with essentially no increase in dispatching time. So let's see if there are any other. Okay, no questions yet. Okay, so if there are no questions, so basically our computational validation concludes that the model is indeed very accurate, even though it makes some simplifying assumptions. So in conclusion, basically what we're using here at a structural level is the expectation of unbalanced dispatches in the SDD system. And that structure then allows us to do look at the expected optimal behavior of the system, and that allows us to do a bunch of different tactical design, address a lot of tactical design questions. And we still get very accurate predictions of what's going to happen at the operational level. So I'm done with covering the material for this first paper. So I will just, in the interest of time, we're already we've gone past an hour. So let me just give you a couple of pictures of what of the ongoing work. So going back to the question about like site dependent.
Professor, it's okay. Take all the time you need for you to fully explain what you want. We'll not restrict the right time. Okay.
No problem. No problem.
Thank you.
So what we're looking at now is the actual deciding of how service regions should be chosen, or the actual size and composition of a service region. And so this would be the place where you would answer questions like, do you have site-dependent vehicles that have to make deliveries depending on maybe the road network or the narrow streets and things like that. So the model here is still going to make an assumption that you have homogeneous vehicles, but here you would include these kinds of restrictions as let's say as initial conditions in this model, but it would be at this level that you would probably do this. So just to give you an idea, this is the kind of output of our current research, which essentially says in the lower left corner you have a depot that is serving this irregularly shaped metropolitan region, and so we have to decide how to split the very large region into smaller vehicle zones, such that a different vehicle is serving each of these zones. And in particular, in this case, what you see is that because there's a travel time from the depot to the farther away zones, those have to be smaller because you spend a lot more time doing the traveling to and from those locations. And essentially what this figure down here reflects what I'm talking about, which is that what we're trying to do in this case is to say how big of an area can a single vehicle serve if it has to serve all of the orders between up to the cutoff by the deadline. And so what you get is you get behavior like this, where the farther the vehicle has to travel, the smaller the zone it has to serve. And so we use an extension of the dispatch time function that I showed you before that explicitly takes into account the size of the service area that this vehicle would serve. And then we essentially throw that into a numerical integration model that tells us how big the service fleet has to be. And then we use some tessellation schemes to get an output like the one that I showed you over here.